Sure, I'd be glad to talk about that. So, the questions on the final exam are mostly short answer. The vast majority of short answer questions. There are a couple questions that involve looking at code, and to a certain degree, those build on each other. But for the most part, they're sort of standalone, and you could kind of start anywhere in the final exam and hit them off. There are a couple true-false. There are a couple complete the sentence. Most are described 3 ways that peer review offers greater flexibility than testing. Or tell me 4 major problems that can come if you don't use continuous integration or something like that. So there's a lot of questions like that. Sort of along the lines of what's on the pop quizzes. Very, very similar. Does that address your question? There is, let me just make sure I'm not saying anything that crept in at the end, or denying something that crept in at the end. There is no code that has to be written. I'm pretty sure of that. Okay. There is code that has to be looked at. No code that has to be written. Other questions?
To what degree are materials covered in guest lectures going to be emphasized? Does it appear on the pop quiz?
Right. They are subject on that. I'm not going to comment on the level of coverage, but they're certainly fair game. Also fair game is the video I asked you to watch in place of today's lecture. So that's not an optional thing. It is something that I expect you to be responsible for. However, my questions about that would reflect the fact that I haven't been here to give it in person, so you won't have gotten the benefit of being able to ask questions about it and so on. But that is subject to testing. So that's that video is on this final component. Systems thinking. Think about causal chains of feedbacks, root causes rather than just symptoms. Altogether, folks, there are far too many situations where people in positions of authority with respect to software projects confuse symptom and cause. I've made that claim before. Give me an example of that. Give me an example where someone could undertake some pretty silly actions by confusing a symptom with a cause.
I have actually.
Good.
That actually happened to us early on in the project.
Okay.
When, the server ran out of memory.
Yep.
Instead, we went bug hunting.
Right. Okay. So that's a good example of where basically you had your efforts misplaced because you misread the situation that was going on. So great example of the technical level. How about the human level? The level of sort of process management, project management.
The project is in crunch time, therefore to increase the amount of output, we put on more and more hours, more and more.
Good. So we're behind in time. We're falling behind. We're falling short of our targets for where we expected to be. So we need people to work longer hours. A very sort of linear, simplistic relationship that, okay, what's needed is more time to make up the lost time, more human time at work. Why could that sort of thing make things worse?
If we work more hours, we eventually build up fatigue, and fatigue causes sloppy code or sloppy testing.
maybe one of the reasons, in fact, we're behind is because people's morale is very low and they're not feeling motivated to contribute. Maybe it's because people are burned out. Maybe it's because people are fatigued. Maybe it's because the code base is really, really unstable. So instead of focusing in on the cause, all too often people focus on the symptom. Another symptom would be, oh, we have too many bug reports. People are not putting out quality code. We are going to crack down, and when bug reports are come about through a peer review session or through testing, we will penalize the author of that code. Again, bugs bad. Lots of bugs are here. We're going to try to change things to quash the number of bugs in a very simplistic way, without asking why is it we are seeing these bugs. Maybe it's a sign of really good testing. Maybe the testers are doing a great job. They're finding these problems. They're draining the swamp, the things that would have caused problems down the road. Maybe it's because there's a lack of communication in the team. Maybe it's because there's some underlying confusions about roles in the team. None of those things are being addressed by the course of action. And in fact, sometimes it may cause bugs to not be reported, which is even worse. You don't even know about them in that case, right? So confusing symptom and cause. There's a lot of cases where people do this. In other cases, we're falling behind. We've got to hire more people. Bring more people into the project. We need more. We need all hands on deck. No more vacations. We can't have the luxury of people taking off for vacations. We've got to crack down on that. We've got to crack down on sick time. We've got to bring more people into the project. And the problem may be lack of coordination within the team. And bringing more people in who need to be trained, need to coordinate with the existing people, drives it even worse into a situation. And one of the cynical truths that unfortunately obtains in these cases is often a manager will make an offer like this to bring in extra people to shield themselves. They're looking for a scapegoat. They're looking for a way to say, look, I gave you everything and you still couldn't deliver. I brought in extra people for you. I doubled our budget and you still couldn't handle it.
That's a strong argument, though, because they are making more. They're bringing in more, yes, but they're not bringing in the right type of more.
Yes, but they can say that to their boss. Look, it's not my fault. We walked the extra mile for this team lead, and they still couldn't deliver. There's something wrong with the team. These things are occasionally done for cynical reasons, and there's a phenomenon known as piling on, which you'll also see in other cases, where a stakeholder who's not interested in having a certain project built will go and request all sorts of features in that project, pretend essentially that they're really enthusiastic about it, and they want it to die. They want to deep six it by just having it be so bloated a plan that it never sees the light of day. That's also been, unfortunately, observed in IT projects.
Why would they do that? Why would they just say, I'm not
Because they have a competing idea. Maybe they want to go with a certain vendor with whom they have a buddy-buddy relationship. Some areas of corporate space, there's a lot of things that essentially amount to kickbacks of sorts. So it used to be quite famous with IBM, where you'd sort of go and you'd want it on your customers. And in the same way pharmaceutical companies do these days with respect to doctors. Pretty creepy. So systems thinking tries to advance thinking tools that help us cut through some of these things. Reasoning about the dynamics, change over time in the system, and think about system structure. And one of the key insights from this is that quality is a systems issue. Product quality is linked to diverse factors. The level of quality of code base affects your agility, your ability to respond to new market opportunities, how quickly you can bring it to market. Costs involved. Think about a project in churn mode where it's spinning its wheels, not really making progress. Post-release service demands. You release a product that has problems, you've been spending a lot of effort servicing that in the field. Turnover. People don't feel good about working on projects with low quality, like the project cancellation, morale, upstream and downstream work. And it feeds on itself. It's kind of a snowball type effect. And feedbacks associated with this have a major impact on software project dynamics, virtuous and vicious cycles you can get in. This is one of the reasons why some projects go bad in a really, really quick time period, and some projects can succeed and overcome all sorts of obstacles. We had an example a couple of years back of a project that we ran into the worst sort of technical challenges, some of them incidentally involving Hibernate, or I think it was NHibernate for .NET, but they were able to overcome these things because they had such high morale, effective cohesion as a team, for example. And yet other teams end up being in a non-resilient state. And one of the biggest dangers here, and you'll probably hear this in the closing minutes of the audio from yesterday, and if I want you to remember one or two things, if I want you to remember 10 things in the class, this is certainly one of them, is that when we have a project, there are these feedbacks that are driving things, and some of the feedbacks tend towards instability, and some towards stability, some towards stabilizing a situation. Now, instability isn't necessarily a bad thing. Companies, for example, thrive on instability in the form of market growth, being able to grow quickly, being able to seize a market opportunity, enhance reputation because of quality breeds quality, because you can hire good people onto a team that's seen as being a really excellent team. So there are some virtuous cycles that you can tap in that have instability. But there are also vicious cycles you can get trapped in. People leaving a team lowers morale. Well, we should really be on this next one. People leaving a team lowers morale, which increases the chance of future resignations. Resignations lead to more hiring-related work, interviewing people, training people, correcting bugs, mentoring new people, which impacts team productivity. Resignations also lead to more of the work being left on fewer people, or more equal or larger amount of work being left on fewer people, which leads again to backlog of work, developer fatigue, lowers morale, leads to resignations. These are very large effects, and one of the big dangers here, and we can weave these into a larger network, involving the quality of the project, for example, thoroughness of testing, desire for quick and dirty fixes, etc. But one of the biggest dangers here, and this is the point that I really want to emphasize, is that there are natural stabilizing features of projects. Features of projects that allow stabilization even in the face of adverse conditions. And in contrast to virtuous and vicious cycles, which tend to be unstable, these are things that maintain an equilibrium. They're kind of like the processes in our body that maintain homeostasis. They keep us in a sort of balance. And they include things like morale-building activities on the part of the team, fatigue-reducing possibilities on the part of individuals, taking vacations, taking sick days, being able to get good nights of sleep, etc. And one of the biggest dangers here is when managers who are ill-informed, who are very short-sighted, who are myopic, when they undertake efforts to try to write a project that's struggling, trying to turn a project around, often they do the stupidest things in the form. And it's not that they are stupid, but they undertake actions which are myopic, which are short-sighted and grievous in their harm. So, for example, they'll not only do things like put extra pressure on for people to work extra hours, which worsens fatigue, which lowers morale, etc., but they will cut back on the opportunities for people to do things like take vacations. They will cut back on the opportunities for people to engage in recreation at work, play foosball or what have you. They will cut back on opportunities for the team to engage in team building activities like going out for a movie together, or every week having some sort of sport activity outside or what have you. These sort of activities are not luxuries. They keep the system in balance, even under adverse conditions. And the risk here is that you, as a manager, there's a temptation to cut them back, to see them as luxuries. But they are the things that keep the project stabilized. So it's kind of like if you were in really bad driving conditions, suddenly going and closing your eyes. It's not going to help. You depend on your eyes to correct for the deviations from the central line. Instead, managers cut these things. They cut them and they put pressure on the wrong points to confuse symptom with cause, and they drive projects into the ground. And if you don't believe me, we used to, in this course, discuss a series of vignettes of projects that went awry. And no, they were not examples from this course. They were examples of major projects, some of which chewed up millions, tens of millions, I think in one case hundreds of millions of dollars. And they led to disaster in terms of the project. Unbelievable stories. And there's a book called Software Runaways, which is about exactly this phenomenon. If any of you are interested, come to my office, you can borrow it. It's absolutely fascinating. Litany after litany of all sorts of different examples, different technologies, different application domains, a common demise. Dostoevsky said of families, he said, happy families are all happy in the same basic way. Unhappy families are each unhappy in their own special way. And so it is with projects that go wrong. I get the questionable privilege of surveying projects year after year in this class. And it's very interesting because different projects attain dysfunction in different fashions. But one thing that you will see very commonly is this issue of myopic managers trying to control at points that are instead symptoms of underlying causes they're not reading properly. They're not reading fatigue. They are seeing a project that's behind needs to be pushed harder. They are seeing too few people instead of failure to coordinate effectively, etc. So this is going to be part of the exam. Any questions on that, since I haven't had the luxury of covering it in class? Questions? Okay, so let's rip through. The charge of the Light Brigade has begun. We're going to rip through some things. So risk management, contingency planning, mitigation are two things I emphasize. What are the differences? How are they different? Mitigation puts into place measures up front which seek to either lower the probability of a risk materializing, in other words, coming about in an adverse way, or lessen the impact if it does materialize. Okay, it invests up front. The contingency planning, on the other hand, puts in place a plan up front. Doesn't actually make the full investment. It puts in place a plan so that everyone's coordinated, so if this happens, if this possible risk materializes, we'll know exactly what to do and we'll do it very quickly. Okay. The other possibility is risk acceptance. You simply accept the risk. Say, look, this is a risk we're willing to deal with. Maybe it's not a very high likelihood. Maybe it's not that maybe it's not that serious as it occurs. Or risk avoidance. You could sometimes do things like get insurance to set aside a risk. You're covered for those risks. Risk exposure I talked about. How do you calculate risk exposure? Risk exposure is something times something. What are those something? Yeah, exactly. What is risk scanning? Risk is monitoring the occurrence of risk for materialization. Specifications. I noted this sort of notion of special specification. These are high-level specifications of what code can be counted on to do. So I expect you to know something about preconditions, postconditions, and invariance held at the method level, for sure. And for classes as a whole, we have these issue of invariance and history properties. Give me an example of a precondition.
Must be above 0.
Yeah, so this given parameter has to be above 0. Good example. It must be non-null, for example. This must be the sole reference, and to the thing that's passing the reference passing is to the sole reference, so that might be a condition, etc. Postconditions. Give me an example of the postcondition. When do postconditions apply? When do we care about postconditions? Okay, yes. Although there's a very important type of postcondition that doesn't require something to be changed. And that is a return value. But then, other than that, there may be an aspect of state change. You've actually fraud this variable, you've changed this, you've displayed something on the screen, you've sent out a message via network, what have you. Postconditions only apply if preconditions are met. All gloves are off, all guarantees are off if preconditions aren't met. Okay. Invariance. I'm going to focus on invariance as a class. We could talk about them for a method as well. Certain things are contained invariant. These two variables always sum to a certain thing. One goes up, one goes down, what have you. Class as a whole, we have invariance and history properties. Invariants are things that are guaranteed to hold at any one point in time. At a single point in time, you can validate whether the invariant is true or false. History property compares things at different points in time. Give me an example of an invariant. Say with a counter. We use the counter class as an example. Value of the counter is greater than or equal to 0. An internal state variable, internal instance variable of this class. The value of the counter never goes below 0. That's an example of an invariant. Maybe this data structure always has at least one key in it, key value pair in it. Never empty. Maybe the data structure is guaranteed to have no duplicates in it. That could be an invariant. Those can be checked, ladies and gentlemen. At a single point in time. No problem. You can check that. You get an assertion that checks that. You should have an assertion. Good thing to check. What's a history property? Give me an example of a history property with a counter. Speak, use. History property with a counter. It compares. A history property is a property about that object over time. So it compares 2 points in time. T1, T2. Let's suppose T1 is before T2. What would be a good example of a history property? Over time, the value of this counter, never decreases. It always rises or stays the same. That's an example of a history property. The number of items in this dictionary can only stay the same or rise. That'd be an example of a history property. Nothing is ever deleted. That could be a history property, right? Another example of a history property is concerns that it's a read-only thing. It's an immutable thing. Why is it good to be immutable? Lecture me, folks, on the virtues of immutability. Yeah, side effects are difficult to reason about. That's one of the key things to cognitive load. What's another thing? I can talk about beauty, but no fun to it, because you might argue that the just take a look. But I'll put aside beauty. What's another reason for immutable objects? We actually talked about it in a big way for one lecture. It's easier to build things out of immutable pieces. Why? That sounds like a strange thing. It sounds like we're building things out of inflexible pieces. Okay, so that gets in, if I'm hearing you correctly, Sage, you're saying something similar in a way to what Alex said. There's greater clarity that this retains its value, and so the programming may be a bit easier, yes, but there's another issue too. If we have, ladies and gentlemen, mutable, if we're building an object, be it a mutable or an immutable object, we're building out of mutable pieces, what do we really have to watch out for? Yeah, so we have to be very, very careful, for example, about handing out a reference to that internal object, or getting in a reference to an object would have to be added internally. We have to clone it. Remember that? Remember that whole thing? We have to go do all this extra cloning work because we are terrified that if we hand out a reference to our internal data structure, that the person outside might be malicious. Well, it doesn't have to be malicious. Might just frob it, might modify it. Remember that? And we don't want them mutating our internals. Similarly, if we're called in the constructor with pieces to build this out of, we now have to clone these pieces because someone outside might have a reference to them. It's actually a lot of extra work. If you can share something, if it's mutable, you can share it. I'm sorry, immutable, you can share it. You don't care if anyone else has a reference. They can't do anything to it anyway. So you can share a lot of common substructure. Non-obvious, but true. Okay. So history property, immutability, a good one, an important one. So specifications, I argued there's a lot of benefits from that. Okay, I talked about subtyping relationship. A is a subtype of B. If we could safely substitute an A where a B was expected. Behavioral subtyping. It needs to behave in every way like a legitimate B. Now, I want you to know this, folks. I don't have time to go over this, but you need to know this well. How would I know if, for example, a method of A, a claimed subtype of B, is indeed a legitimate overriding of a corresponding method of B, which has the same name and same signature, or similar signature? How would I know if it's a legitimate one? Remember that whole thing where we said, well, the supertype, how if this method in the supertype can take a string, or can take an object, can the thing in the subtype take an object as a parameter? So method foo in the supertype, can take an object. Could the subtype, for example, a subclass of that kind, could foo there take a string? Yes or no?
No.
Why?
Because we can't substitute. If we were to instantiate A, we wouldn't be able to use that method call whether we would otherwise call it.
That's right. That's right. So if we have the subtype that we can pass around as if it's an instance of the superclass, bereft of chalk in the front. We can pass it around as if it's an instance. We can subtype A, supertype B. Did I give those consistently? Yeah. And we have foo up here. It takes an object. And we have foo here that takes a string. And we pass one of these guys, one of the A's, around as if it's a B. Could bad things happen? Yeah. We could call it at any object. And suddenly refusing it, saying, that's not a string. Wait a minute, this thing doesn't require a string. Remember this whole thing with FedEx? If I'm setting up a FedEx franchise, I've got to play by the FedEx rules. No, I may go the extra mile beyond the FedEx rule, but I at least got to accept packages. If FedEx accepts them by up to as late as 10 a.m. in the morning for delivery at 5 p.m. the next day, I've got to accept them at least up till 10 a.m. Maybe I accept them till 2 p.m. That's fine. So there's a relationship here between what you can accept for methods in the subclass versus in the superclass. And then types, for types of the return values you got to think about, right? So let's suppose this one in the subclass, this foo here, can take an object. Is that okay? Foo object, yeah. How if this one returns this one in the superclass or super type returns a string? Could this guy in the subclass return a string? Would that be okay? Yeah, you do that all the time in Java, right? It could return a string. Okay, if this one returns a string, could this one return an object? The answer is what? Think about it.
Again, we can't substitute calls to an instance of A, calls to an instance of B.
Correct. So if someone up here were calling it thinking it's a B, they're counting on, this is an aspect of postcondition, they're counting on getting a string back, and suddenly they're getting back an arbitrary object. Now, could this one return, could this say object, and this returns a string? I'm not asking whether Java accepts this. I'm asking logically, is this acceptable? If this one only promises that you'll get an object, and this one promises a string in particular, is that okay? The answer is yes. Because a string is a legitimate object. You shouldn't be surprised if you get a string. That's perfectly legitimate for the superclass. As far as the superclass is concerned, here we can be more specific. And similarly, ladies and gentlemen, for exceptions, you can go look at the slides for more information. But you need to be comfortable with this, okay? You need to be comfortable with this. And this is all about polymorphism. So I talked about the Liskov substitution principle. If there's a property that's provable about B, if someone looking at the documentation about the supertype could convince themselves reasonably about some property, maybe it's that it never declines, maybe that it's immutable, maybe it's something about it, what values can accept as parameters, or what it can return, or that collectively it can never have a null value. Whatever property you can plan about you need to maintain that property about a subtype, or else you will rudely surprise. You will cause a bug because someone may be reasonably counting on that property. And ladies and gentlemen, if you don't want to make that promise in your supertype, if you want to design an interface or class where it can be flexibly subtyped, for example, subclassed, without any sort of strong assumptions being made based on inference from the names of the methods and so on, you could put a declaration that, hey, you cannot, this class may look immutable, but do not count on that. That's also okay. It's just that if you can develop confidence that there's some property that holds about the superclass, then if someone could reasonably come away with that confidence, then you've got to adhere to it in subtypes. Does that make sense? Otherwise, you can break code that was written long before you ever created your class. Liskov substitution principle is not being picky. It's actually using common sense and being systematic about and consistent in our common sense, okay? And there's three components to it. Method signature compatibility, we were talking about that here. Methods of subtypes must behave consistently with those of supertypes. You can't have a square root declared in the superclass suddenly have a corresponding overridden method that does a cubed root or something like that. And the subtype interface must preserve provable properties of supertype in terms of, for example, invariance and history properties. So we also talked about subclassing. So the difference here with respect to the Liskov substitution principle, the whole issue is about promises. Making sure that we're dealing with in the world of promises. If we make a bunch of promises, implicit or explicit, for the super type, we need in subtypes to adhere to those same promises. Now we can implement them in any sort of different ways, but we need to adhere to those promises. We need to be consistent with those promises. We need to live up to those promises. we need to hold true to those promises. It's just like if I'm a FedEx franchise, I need to live by FedEx rules. Okay? People come to me thinking I'm just any old FedEx franchise, and I need to at least live by those rules. I may be more accepting in packages. You know, for example, here, if we had, ladies and gentlemen, I'll give you one more of these. If this thing accepts a string, could I accept an object here? The answer is, because I could call, if I pass this in and I call it with a string, someone's expecting it's one of these, that's fine. This doesn't say what happens if you don't pass it a string, basically. If it's handled here, well, that's okay. It's not a bad thing. So this is actually legal. We could relax FedEx rules. We could say, well, we'll accept packages till noon, except just till 10 a.m. Still promise delivery by 5 p.m. the next day. They'd still be happy. They'd have no reason to be unhappy. That's all about promises. Liskov substitution principle. We also talk, ladies and gentlemen, about subclassing, which is about more than promises. What is it about? It's about what, ladies and gentlemen? Yes, it's about reusing implementation. It's about inheritance. And that implementation could include methods. It could include instance variables. It's about reusing how we implement promises. And here we have stricter specifications. And to cut to the chase, remember this guy with add all and add. Remember that? This example was in large part motivated by the desire to show, in concrete terms, a situation where you need to know how the superclass works. Here we're creating a subclass. And so we're using the implementation of this guy on the left. The subclass is on the right. And in order to build this subclass in a reliable fashion, in a fashion that will work up front and that will continue to work going down the road, we need to know something not only about how this superclass works right now, but what's promised for the superclass from now on, what it adheres to in terms of how it works. We need to know, in short, something about the implementation of the superclass. Give me 2 examples of information that a subclass might reasonably want to know about the superclass in order to confidently implement a subclass that won't break mysteriously whenever the superclass is evolved. It's implementation. What sort of things might a subclass want to be promised by the superclass? Yes. Yeah. So, does add all call add or not? Remember that? Really, really important. Because if we want to create a subclass, the instrumented asset that records, for example, how many things we've added, how we implement that, whether or not a given implementation of the subclass is correct, depends on whether add all in the superclass calls add in the subclass. Calls add. So that's one piece of information. Another piece of information we might want to know, and I don't think it is listed in these review slides. It's an issue of suppose you have getters and setters in the superclass, for example. You might want to know, okay, what things do I have to override together? So if I override get, probably I have to override set as well. Because get reads from a variable, sets that variable. And if I override one without the other, it's incomplete. I can't expect it to work. I need to know something about how it works under the hood. In other words, which set of methods are kind of manipulating underlying variables together. So if I want to replace one, I've got to replace a block of it. That's another sort of thing that we might want to know. But the clearest one is what calls what. No, although it can in some cases be, but there are cases where, for example, a get doesn't call set and vice versa.
but they have to be placed together because they're frobbing the same underlying variable. Okay. But you're right, Alex, that there are other cases where, there's a method which calls get, for example, and I gave an example. It calls get, and whether or not it calls get or just reaches and reads the underlying variable matters a lot, because if we override get, do we automatically fix this other method, or do we have to override it as well? If it's just calling off to get, we override get to use our instance variable instead of the original one, then that other method might work just fine. But if it's frobbing, if it's reading that underlying variable itself, overriding get won't help. We got to override it as well. Right? So maybe there's a method get, set, and increment. Does increment call get and set? It just depends on get and set. If so, if we override get and set to use a different underlying variable, then increment automatically works. On the other hand, if it is reaching in and grabbing the variable itself and changing it and writing it back in directly, overriding get and set won't change it, won't update it to use our variable. Instead, we have to override it as well. So there's some examples of that in the slides. Safest subclassing is avoid it, declare a class final, for example. This is not a bad idea if you're not planning for subclassing. You can also use wrapper classes. And I don't have time to go into it now, but I'd urge you to go back and listen to my slides. Wrapper classes look a bit ugly, passing on these calls, but they can avoid the problems of subclasses. They don't exhibit the yo-yo problem, which is associated with subclassing. Here, you have this instrument that's set, and it just passes on. Here we have an instrument to set, and we can declare our methods add all, get, add, count, and we're just passing on calls after a little bit of work, potentially passing them all onto some internal set. We're not overriding those calls, so we don't have to worry. We're implementing the set interface, but we're not overriding any calls of an existing class. So we don't have to worry that any of its methods will call some of ours, or that we're depending on internally on how its methods work. We could simply delegate where possible. So wrapper classes will get you out of the conundrum with classes. Okay, we are in the sort of sudden death phase here. So I've got to push on here. So I noticed interfaces are more stable than class-based inheritance. You can implement several interfaces at once, whereas class-based in languages like Java, it's single inheritance. Double inheritance leads to complications. You're not responsible for that. So it's actually a good thing to understand. You should know it's tricky. It causes problems, okay, to reason about multiple inheritance. Skeletal implementations are something I talked about. And in fact, we saw this in some of the code that we talked about in class. So here we have a skeletal implementation and an abstract list. It implements lists, and we just fill in these methods, for example. We fill in some existing methods of this. And it turns out that skeletal implementations can be used to enhance sort of mix-in-like functionality. And I have some comments on these. They can kind of give a lot of the benefits of subclassing without many of its risks. Okay, fakes, mocks, and stubs. Mocks, we talked about them yesterday, so I'm not going to talk more here. Value objects, we talked about some of those things. Defensive copies, what you have to do with mutable objects, and objects as building blocks. Testing, oh man. Talked about some testing metrics, fault feedback ratio. What's the fraction of bug fixes that lead to another bug, for example? View of testing is more than finding bugs. It's testing solidness, how nice a user interface is. Testers are on the front line to realize how acceptable often a program is. Yes, testing needs to be done both by developers and by by testers for sure. What sort of testing is often done by developers? Unit testing, very commonly, unit integration testing, some amounts of integration testing. Testing typically done by testers includes system-wide tests, acceptance tests, for example. Automated testing takes a lot more effort up front, and like often, say 10 times as much to get a test established, and then you have to maintain it even as the system evolves. If you have user interface testing, the user interface often evolves really, really quickly compared to the rest of a program. You're changing things there, and depending on your abstraction layer that you use for user interface testing, you may find yourself having to fix the test very, very frequently. Bug classification, severity, priority, for example. Prioritizing testing by risks as one sort of metric by which to prioritize them. Impact of separation of concerns on testing. Testing and peer review and who is doing testing. Estimating undiagnosed defects. I was glad to see that today. Test hooks. Well, we talked about some of these yesterday. Test harnesses and test stubs. Testing object-oriented code. I had a lecture on that you're responsible for. Coverage procedure. These are the 3 big steps for coverage. We identify the set of things we need to cover. We develop a set of paths that include all of the things we need to cover. These should be legal paths from a legal start point to a legal finish point. And then we develop a set of concrete test cases that test that test these paths. And in general, a given concrete test case may test multiple paths, and a given path typically includes many things we want to cover. For example, many nodes or many edges, many transitions. CPM diagram, CPM algorithm, you should know how to run it. Estimation, use of range estimates. The fact that range estimates tend to be too optimistic, but they can help set expectations. Peer reviews are a variety of functionality. How do they differ from each other? Preparation of work ahead of time, for example. Dissemination of information, stage roles for different people. Follow-up following the review meeting, for example. These are different ways that the reviews differ from each other, okay? And I think those are covered in my slides. They're covered in my videos. Quality coding, we talked about this. You saw me go through various types of grimacing associated with these things. So hopefully that should be burnt into your memory pretty well. Systems thinking. We've done it, ladies and gentlemen. It's 4:58. I have 2 minutes to answer further questions, and then I'm off to 394. Yeah. I'm sorry. So you were asking about from 394.
Yeah.
Okay. Sure. They're actually posted on 394's website, but I'm sorry, Robin. I was thinking you meant the slides from yesterday's peer review session. I'm sorry, yesterday's review session. I will post those slides to 394 on 371 as well.
Thank you.
Okay. Sure. Yes. Sage.
With